we have the 220 line comes to this point, and through this line the 220 comes from here to this point. And as you can see that here we have a fuse and an MOV. So these two are used to protect the circuit from any high voltage, and this MOV also protects the circuit from any high voltage surge. So next the AC comes from the through this MOV into this filter cap over here, and then to this thermistor over here. Then there is a bleeder resistor, and then another filter cap, and then the inductor. This is the 0.7 millihenry inductor. And then we have this main switch. This is actually a 4-pin switch, and through this switch the AC comes to these two parallel inductors. These are the 100 microhenry inductors. And then through this filter cap, this comes to the AC comes to this inductor here. This is 6 millihenry inductor again. So we have this again, another capacitor over here. Then the AC comes to this bridge rectifier. So the AC, after so much filtering, is now converted from AC to the DC. The DC then comes to this to these two capacitors over here, and then through these capacitors the DC comes to this circuit, and this circuit is actually known as the power factor correction. And the IC that I'm using here is the MC34262. And I may just go into a little bit depth of how this IC actually gives us a power factor of up to 9 or 0.9 or 0.95 or even 0.97. So I may tell you that in the end of this video. And here this is a ferrite core transformer, and this transformer is part of this circuit for the power factor correction. So after that you can see that we have this the 400 volts from that point come to this point, and the 400 volts is then divided into this section that goes directly into the main transformer, and the other 400 volts is also sent to this auxiliary power supply over here. And this auxiliary power supply is actually used to just turn on these IC over here, this one and this one. I have removed this IC because it is for the voltage protection and the current protection. But right now since I was working on some projects, so I don't needed that voltage or current protection, so just I removed that IC over there from there. So next, this auxiliary power supply, to tell you a little bit about this. This auxiliary power supply is actually a flyback scheme. I have used the flyback topology for this power supply because I just wanted to use a single IC to turn on this supply. And here I have used this is the I don't know if you can see this. This is a top 222Y IC. It is not actually a transistor, it is actually whole IC, and within that IC we have the FAT. So this IC actually gave 100 kilohertz of signal to just convert the DC 400 DC to square wave AC, and to also to just make this ferrite core transformer to work. After that we use some turn ratio such that to convert this to just step down the 400 here to this 12.5 volts. Actually I have used 13.5 because 1 volt is dropped across this rectifier over here, and we can't use simple rectifiers over here because since this is high frequency signal, so we have to use fast diodes like the 414H, or other than that there are a lot of other fast diodes in the market. So next, as I told you that this auxiliary power supply is used to turn on these ICs because these ICs have to be turned on so that we can just make this whole power supply to work. So we use this auxiliary power supply to turn on these ICs, to turn on this voltmeter and ampere meter over here, and also this fan over there. So after that this 400 from there goes to this point, or also this 400 volts over there is actually I have center tapped so that I can give half of the voltage to this main transformer over there, because I've used the half bridge topology there. So this transformer is actually driven by these two FETs over here, and these two FETs actually been driven by this main driver transformer over here, and this driver transformer in turn is driven by these 4 transistors, and these 4 transistors are in turn driven by this IC. It's the TL494 IC, and actually we can't just use the signal from this IC to drive these FETs directly, because since we are just working with high voltage over there, because so we can't just use the high voltage and connect this signal to these FETs, because it will definitely blow up this IC over here. So this IC is generating here 35 kilohertz, and it's very simple. We just need to use a simple resistor and a capacitor, and depending on those values of the capacitor and resistor, it generates a specific frequency signal. So that square wave from there goes to these 4 transistors, and these 4 transistors give the signal to this driver transformer. This driver transformer in turn generates a square wave 12 or 13 volts signal that goes into the base gate of these MOSFETs over there, and these MOSFETs in turn drive this main transformer. So it was pretty simple. I hope that you understood that how the IC is turning on these on and off these main FET MOSFETs over here, and help this main transformer to generate the output DC output square wave signal. Okay, so after this, since this 135 volts is being provided in the form of square wave to this main transformer, so the output will also be a square wave. So I have just winded this transformer in such a way so that it can give round about 17 or 18 volts output, because there is voltage drop across these rectifiers over here. So that we have to keep in mind the voltage drops over the across the diodes. So the output from this main transformer goes through these 3 wires. It's actually center tapped, so the 2 of the wires goes into these 2 rectifiers over here. These also fast rectifiers, and one of the wire is the black wire that goes to this at this point. So the output of these 2 rectifiers is being joined beneath this board, and the single wire goes into this 14 microhenry inductor. This is actually 14 microhenry inductor. Output from that inductor goes at this point. I hope you can see it clearly, and from that the output then goes through this capacitor and these 2 capacitors to this inductor, where this is another inductor. This is a 0.5 microhenry inductor. Then this output of this inductor goes through these resistors at this point. So the purpose of these resistors are actually for the current sensing, and so that we can actually see how much current is being driven through this power supply, and just show it on the ampere meter. So output from these 2 terminals goes through these wires to this 2 terminals, main terminals over here. So this was all about this power supply, that how it is actually working. And this is an op amplifier IC. There are actually 4 op amps within this IC, and I have used 3 of them. One of them is not being used, and this is a NOT gate IC, so that it can be used for the protection, voltage and current protection for this power supply. So now let's just talk about this voltmeter and ammeter over here. So as you can see, This is the ampere meter and this is the voltmeter circuit. These ICs are the ICL7107. It is actually analog to digital converter ICs, and there's an oscillator within that IC. Also we have this ICs. These are two ICs which are the ICL7660, and these are actually to provide the negative voltage -5 volts to the pin 26 of this ICL7107. These are the simple regulators 7805. And next, this is a variable over here to increase or decrease the voltage, and the these comes to this wires from that variable come to this point. And finally, one more thing that I want to show you here is if we just flip this power supply, so we can see that there is another switch over here which says fixed voltage and the variable voltage. Right now it is just switched towards the variable, so that I can use this variable over here to increase or decrease the voltage. But when I just switch this turn this towards the fixed, then this variable is can't be used to increase or decrease the voltage, but instead we have another variable at this regulator, sorry, at this here, and it was yes, this one. So I just fixed this regular variable to 12.5 volts, so that whenever I want to use any 12 volts or 12 volts thing to just turn on by this power supply, or just charging any battery, so that I don't want to just set that voltage again and again by this variable over here. I just have to just change the switch position, and I will get fixed 12.5 over here. That's all from this power supply, and I hope that you understood that how this power supply is actually working. This is the data sheet for the MC34262, which is the power factor controller IC, and you can easily download the data sheet from the internet, and I suggest you to study this data sheet in detail before designing any power factor correction circuit using this same IC. So if you just came a little bit down here, you can see this is the internal block diagram for this IC, and there is not a lot of things within it, but it is really an efficient IC for the power factor correction. And you can see that it's an 8-pin dip chip IC, and we have the voltage feedback input, compensation, multiplier input, current sense input. Here we have the VCC, the drive output, ground, and zero current detect input. So it's really simple to design the power factor using this IC, and you can see we have the maximum ratings for it, and stuffs like that. So you should download this data sheet and study it in depth to get a more detailed understanding of how this actually works. So I will just explain it to you, the main functions of how this helps in increasing the power factor. Okay, so first of all, as you can see, we have this circuit over here, and it is not using any power factor correction circuit, as it's written uncorrected power factor circuit. So we have the AC line input, which may be the 90 volts up to 260 volts AC, and the AC then being converted to DC using the rectifiers. Then we have the bulk storage capacitor for our DC to DC converter over here, and finally we connect our load over here. So the problem with this circuit over here, if you are not using any power factor correction, is that as you can see, we have this AC 50 Hertz signal, and at its every peak value, either it's the positive or the negative, at its peak value we are drawing a lot of current, and due to that current we are actually facing the line sag, which what it actually do is it actually pulling down this signal and the voltage a little bit, and it's not a really good thing at all. So we have to get rid of this problem, and to keep the line and to keep this signal without getting this line sag, we have to introduce the power factor correction circuit. And here you can see we have introduced this power factor correction between the rectifiers and the bulk storage capacitor. So you can see there's also introduced a new capacitor, which is the high frequency bypass capacitor. And if you remember that after the bridge rectifier in my power supply, I had the 3.3 microfarad 400 volts capacitor, and those were actually the high frequency bypass capacitor. So if we just have a look at this circuit over here, we can just know that it is actually a boost converter, DC to DC boost converter. We have this MOSFET over here, the series resistor, and the source pin of this connected to the negative rail through this resistor, and we have the drain connected through this inductor to the positive rail. So this is the MC34262, and you can see after that we have the same bulk storage capacitor and the DC to DC converter over here. So, and also we have to just keep in mind that since we have to use a diode over here, so we have to use a diode such that it can sustain high current that this DC to DC converter draws, because all the current is drawn through this diode, and we have to use diodes like the MUR series. So let's just come down and see what how this circuit helps in overcoming that line sag problem. You can see that we have the half sine wave, 50 Hz sine wave. First of all, we were having the problem of line sag at the at every peak value, and a lot of high current is being driven. Due to that, we had the line sag problem. But now, after introducing this power factor correction circuit, so whenever this MOSFET is turned on, you can see that we are drawing current, but it is not high enough to just introduce that line sag. And after that, when we are just turning off that MOSFET, then the current driven is then goes back to the zero. After that, whenever the MOSFET turns on, it draws current, but it is still that current driven is not enough to introduce that line sag problem. And after that, it whenever this half sine wave is completed, it actually averages the value of the current, and we get this another kind of a sine wave. And here you can see there is no problem of line sag at all. So this has actually removed the problem of that line sag problem which we're facing before if we were not using that power factor correction circuit. So and just come down a little bit and see the application information. And here are some first of all, this is the design equations. This really helps you people and designing power factor correction circuits. And here you can see there's a lot of stuffs required: converter output power and peak inductor current, inductance. It tells you a lot of things, and it is really not so difficult, because you have to just move in series to finally get the all these things that you need to design this power factor correction circuit. So, and this is the first example they have shown you. This is the 80 watt power factor controller. You can see we are giving 92 volts up to 138 volts, and to passing through this RFI filter and bridge converter. When we get this DC over here, we have this capacitor over here, high frequency capacitor. And this is the MC34262 IC. We have this remember that I told you that we had this inductor, and we have to convert this inductor to transform. It is actually a transformer right now, because we have the secondary winding, so that it can just sense how much current and voltage is being used at this point. Okay, so it can just stabilize the voltage. And also there is another feedback. This is actually a voltage feedback over here. And there's the MOSFET over there. The gate is connected to pin 7 of this IC. And here we have this power diode, which is the MUR130. So if we come to the details of this circuit, you can see that if we are giving the input voltage of 90 volts AC or 138 volts AC, but still we are getting fixed voltage of 230.7 down to this value. And you can see the current is also same. And the power factor, you can see the power factor for this value is 0.999, and the power factor value reduces as we increase the input voltage, and the efficiency also increases as we increasing the voltage. So you can see that it actually it is working really well, and it is just protecting the circuit from any voltage ups and downs. So here's another example. You can see here, this is the example one for the 175 watt universal input power factor controller. The circuits are all pretty same, and just a little bit of changing in this transformer and maybe in the sense resistors. And you can see, other than that, all the circuits will be the same. Okay, and you can see that we are getting actually 400 volts for the universal input of 90 up to 260 volts AC. And in the details you can see that if we are giving 90 volts or up to 268 volts, we are getting the same output voltage of 402 and down to this value, and the current is also same. Efficiency increases as we are increasing the voltage, and also the power factor reduces as we are increasing the voltage. So they have also, you can see that they have also told you that which coil they have actually used over here is the Coilcraft N2880A, and they have told you how much primary turns and which wire gauge is being used for the primary and secondary turns over there. And also the primary inductance is also another important factor in this, and also the gap that we actually give between the two ferrite cores. And finally, this is another circuit over here. You can just see it. Here we have some graphs which give you detailed information about this. So it is a really cool stuff, and you should download this data sheet and study it in detail. And I really suggest you to study it in detail before just trying to build any pre-converter, power factor pre-converter. So I hope you understood all the main things, that how this IC is actually working, and also this my power supply, that how that power supply was actually working.